Hey ladies and gentlemen, my name is Funkster and I'm here to sell you some great noises. I got triangle waves, I got sawtooth waves, I got square waves, I even got some sine waves, but they're not quite as cool. So, anyways, I am here to talk about the wonderful world of analog synthesizers and the fun little bits that go into them and the various ways you can plug them and glue them together and do fun things. So let's look at how analog synthesizers work. Thank you, enjoy the pizza. All right, so this is my warning slide for this is a really, really deep subject. And there are times in here where I'm gonna be a little bit hand wavy and a little bit just I'm gonna throw some resistor dividers up on a thing and not put numbers on them like a terrible person. And you can just figure out your own voltage divider math later. So yeah, there's a lot here. I got a little bit of time, so there's gonna be these gloss over parts. I'm just gonna be woo, magic. Some assumptions, because I know we all like assumptions, I guess, or something. Hey, I'm assuming that you all have some basic electronics knowledge. I can talk about resistors and capacitors and things like that, op amps maybe and comparators, and you all know what I'm talking about, right? Yeah. Sweet! I like that in an audience. When they know what I'm talking about, that makes for a much better presentation. I'm also kind of assuming some basic music knowledge here. I can talk about octaves, I can maybe talk about semitones and decibels, and I'm not going to get into weird, jazzy G minor 13th edition chords or anything like that. But if that's your thing, that's cool. I dig that, man. I'm way into that too, but I'm not getting into that in this presentation. So, moving on. Here is what, in fact, I am going to talk about. I'm going to talk about operational transconductance amplifiers. They look like op amps, but they do not behave like op amps. Do not hook them up like op amps. It will end in tears. And then we can do all sorts of really, really fun things with those operational transconductance amplifiers. We can make noises, we can make amplifiers, we can make oscillators, we can make filters, we can do all sorts of weird, noisy things with electricity. It's great. And then towards the end, I'll get into how we glue it all together. There's a lot of hand-wavy gluing it all together, pieces plugging into stuff with all the cables patching and modular synthesizers, because we've all seen that with the giant rack of modulars that have 10 million cables going from here to there. It's how we get sound from point A to point B. And then there's all sorts of other cool things that I'll briefly discuss at the end that makes analog synthesizers even funkier. We like funky. Our friend, the operational transconductance amplifier, looks like an op amp. It's not an op amp. What this does, essentially, is it takes our input voltage there, it takes that difference, and it puts out a current. Not a voltage, a current. But it does that based on, this diagram calls it I-ABC. I usually call it I-control. The ABC, in this case, stands for amplifier biasing current. This allows us, essentially, to change the gain of the amplifier arbitrarily. We send some amount of current into that control pin, and that determines the gain of our amplifier. And there's a lot of math around that, but for the most part, it's our transconductance, what we call GM, is going to be about 19.2 times our I control for a very specific subset of realities that we're interested in.
Exactly 19.2?
Roughly. There, I'll put a little audio operator in front of it. So we send some control current in there. This then does some amplifying based on the VN pins and sends out a current. It's a really cool device because it means that we can use this to control the gain of that, which, hey, look, if we convert a voltage to a current there, what do we have? We have a voltage-controlled amplifier. It's really neat. It means that I can send a whole bunch of voltages and it will do different things, and I don't have to touch any knobs or dials or do anything else. I have all these automatic signals that will control it for me. It's really cool. So yeah, that's an OTA, and part of the reason that you don't really see these in anything else is that there are a lot of really, really crappy limitations about this device. For example, the input range, the VN plus to VN minus, it's only linear up to about 20 millivolts of difference. And outside of that, it's got this really weird hyperbolic tangent curve gain thing going on. And some of the newer ones have this I-bias pin that you can kind of extend that good linear input range up to like 30, maybe 35 millivolts. I know, it's amazing. And then, yeah, your I control current input range is anywhere from like 0.5 microamps to 500 microamps. It's a pretty wide range, and that gives us cool, like 1 to 1,000 range. That covers most of, like, if we're trying to cover 20 hertz to 20 kilohertz, hey, that's a 1 to 1,000 range. It works out pretty well. So that's pretty neat. The output impedance is pretty terrible. So if you're trying to like drive something with it, it's not going to work out. You're going to want to buffer it and like give you some better actual amplifier characteristics there. And also the input impedance is pretty terrible. It's like 20 kilo ohms. It's not really like, you got to drive it with some force to get it to do what you want it to do. But anyways, this is the operational transconductance amplifier. It serves as the basic component of most everything in the classic, Moog, Buchla, EMS, whatever analog synthesizers. Bob Moog especially loved these, like the CA3080 and the CA3082, and tried to put them in pretty much everything. I should mention this is also absurdly temperature sensitive, and a lot of the really early analog synthesizers had heater cores to like bring them up to a known stable good temperature, because it was just like everything worked better at like 50 degrees Celsius. This is the main OTA still in production. There are probably other clones of this, but like the 3080 is long since out of production, the 3082 is long since out of production. The LM13700 is a nice dual OTA that's still in production you can get. They've done some like device physics magic to it to make it better somewhat than the more classic OTAs. It's pretty neat in that regard. You'll see some fun buffer devices towards the end there, and that's because, again, the OTA generally has a really terrible output impedance, and so you want to buffer it up if you're trying to do anything useful with it. So you'd have the current output, you'd run it through a resistor to convert current to a voltage, and then like buffer the voltage, and then you have a voltage out. But yeah, we don't use those all that often in analog world because we want that current. We don't want the voltage. We just want to like feed a current into a thing and call it good. Anyways. Now we're going to build some things with those OTAs. Just got sued by John Cage. Here's where I whiteboard stuff because I like drawing. We are going to build us, we talked about building a VCA with an op amp. It's pretty straightforward. We have something that converts a voltage into a current for us, and we drive it into that I control pin of an OTA. It's pretty neat. Now we get to do the really fun stuff, which are voltage-controlled oscillators. We like voltage-controlled oscillators. Oscillators are pretty cool in general. You can turn a trim pot and have a 555, make some weird noises. That's great. 555s are cool and all, but you got like 1 octave of range. Boring. Anyways. So I talked about this magic equation, and I'm going to completely ignore that for now. Chris, I don't know if you have enough paper here. I'm going to like burn through all of this. There are 2, excellent, thank you. There's spares if I need them. I'm going to come back to that. It'll be useful later. There's 2 sort of classic voltage-controlled oscillator cores. When you think oscillator, you're usually thinking like a resonance feedback oscillator or something that produces like, whatever, a sine wave. One, it's really hard to control those with voltage. It doesn't it's a mess. It's bad, it doesn't work out too well. Also, this is really boring. Like, have you listened to a pure sine wave? There's nothing going on. There's nothing musically interesting about a pure sine wave. It's really kind of tame. The classic Moog synthesizer cores were all based around a sawtooth wave. And this is fun. This is basically a thing that goes up like that and then resets and then goes up like that and then resets. And yeah, this is all sorts of wonderful, delicious, delightful, amazing, gritty, raw harmonics that really make things musical. We like those raw, powerful harmonics in our sound. And it turns out that's really easy to do. And it has nothing to do with this like phase shift resonance oscillator thing. We don't care about that. We can do that with what's called a relaxation oscillator, which I'll get to in a minute. And then the other school of thought in a lot of oscillator world is the triangle core, which Buchla did. And this is basically just like, again, this looks a little bit more like a sine wave, but it's still got some nice raw, rich harmonics that we really like. And also, it turns out it's really easy to turn either of these into a square wave, also very useful. Fun thing about the sawtooth is like you can have a sawtooth go down as well. For our ears, it doesn't make any bit of a difference. These have the same harmonics. We don't care that much. If you're trying to like use this to control something like a frequency sweep or something like that, this is the rising frequency sweep. This is a lowering frequency, so it's like woo, woo, things like that. So those are some fun waveforms because we like waveforms. They make noise. To make those, we're going to use what's called a relaxation oscillator, which is basically just letting a capacitor do its thing until we tell it to do a different thing. And speaking really high-level magic, we have some like control voltage in. This is the voltage that sets our frequency. And we're going to run that into like a pretty simple integrator circuit. And there are many ways to make an integrator, and I'll get to one in a second. But so all this is doing, like this is DC voltage, that means that this is just going to kind of go up like that. And then we're going to run that out to a comparator against some threshold voltage. And that's going to hit a reset thing here. So, it's going to rise, hits a threshold voltage, resets, rises, hit the threshold voltage, resets. And hey, look, if we increase this voltage, this rises faster and then resets, and rises faster and then resets. And if we drop this way down, it's going to rise really slowly and then reset, and really slowly and then reset. So, hey, look, we now have a voltage-controlled oscillator. And it turns out this is really, really easy to build. The most basic integrator of all is that guy, right? We have a voltage input here. This resistor turns it into a current, starts charging up the capacitor until the op amp can do no more. But here's the cool thing. We take that comparator over here, tie it to a reference, have that hit a thing like a JFET right there that shorts out that capacitor and essentially resets it. What was that, 5 parts? 5-part voltage-controlled oscillator. Pretty cool, huh? We can use the OTA to similar effect. We can do a similar thing with an OTA, right? Because we take an OTA, we have some, whatever coming in. We probably have some like constant DC coming in here, and we have our control going in there. And this is spitting out a constant current for us, which, hey, we can use to charge a capacitor. Right, so that's charging up a capacitor, same idea, goes off to a comparator, right? That comes around here and hits, look at my amazingly drawn JFETs because, yeah, right, same idea. So those are both very cool ways of making a pretty straightforward sawtooth wave generator, right? It's just going to keep ramping up until it hits that reset, and it's going to slam back down to ground. It's going to keep ramping up until it's that reset, and slams right on back down. The other cool thing, right? So we got this guy. We got a sawtooth wave coming in. It's pretty easy to turn that into a triangle wave. We just, run it through a cap real quick, make that our DC, and then put that through, a rectifier. Suddenly we got triangle wave. Throw that into a comparator real quick and you have yourself a nice square wave. So there's some really easy ways to take that sawtooth wave and then do other fun things with it. And then depending on this, I've been doing the ramp up example, but you shift your signs and your control voltage or your control current. You can do the ramp down example. Doesn't matter too much with your audio band VCOs, but if you have a nice like low frequency oscillator that's doing a filter sweep for you, then yeah, the direction of that sawtooth matters suddenly. So you have some choices there. Am I being hand wavy enough for everyone? So that's the sawtooth wave generator, and that's the core of most of like the classic Moog synthesizers. And the Moog school has kind of become dominant. But the Buchla core stuff, Buchla decided he wanted a triangle wave. I don't know if any of you know the history of like Buchla versus Moog. Moog is East Coast, Buchla's West Coast. There you have, that's the conflict right there. It's done. But Buchla built all of his synthesizers around this sawtooth core generator. And these are a little bit trickier, but not by much. And so I'm going to, again, like start super high level and dig down deep a little bit. How am I doing on time? All right, I'm going to just keep talking until you tell me to shut up. All right, so basic idea here. We're still going to use an integrator again because we've got these nice ramps that we like. But I want it to go up and then down, and then up and then down. So I'm actually going to have like a positive V in and a negative V in. And I'm just going to put a little switch here and throw that into the integrator. And that's going to go, again, into a nice little comparator over here. But what I'm comparing against is also going to switch, right, to reference plus and reference minus. And so that's going to do its magic as well. This is going to send me an output that I can then send over to this switch, send over to this switch, and then when this toggles, it'll change both the reference and the voltage source. And that means that this guy out here is going to do a cool, or sorry, not that, this guy here. That guy there is going to give me a cool triangle wave. The fun thing is that this guy here is actually going to give me a really neat square wave. So bam, 2 for 1. It's a good sale, right? Get 2 for 1 waves. It's amazing. No more hardware required. So that's the basic model. And a lot of that's essentially the same as what we just looked at, except we're going to do some little trickiness. We're going to take an OTA up front. This, by the way, I forgot to talk about this. This is the magic that tells you it's an OTA, this little current source in the front of the triangle. That's how you know it's not an op amp and you can't wire it up the same way. And just throw something out here, little unlabeled resistor divider, because we like unlabeled resistor dividers, and that's just going to go to ground. I'm using my grounds atrociously loosely as well, so I'm a terrible engineer, and you should not listen to me. This is going to charge up a capacitor, like we talked about, but there's no reset mechanism. We're not concerned about that. We're going up and down. And then we're going to buffer this output, because, as I mentioned, the output properties of an OTA are terrible. So buffer that output real quick. And then we're going to throw that into another OTA, because we like using OTAs. They're really neat. By the way, this is where our voltage control comes in. I'm going to label it current control for right now, because OTAs are current control. By the way, I'm being a little hand wavy about the current control for a moment, but don't worry. I'm going to get back to that magic glue in a little bit. So we have this essentially is our integrating structure right here. And we're going to then tweak out another OTA to be our comparator for us. Throw another thing there. All right, this is a thing there, and then I'm going to clamp that with some diodes. Yeah. Hey, look at that. It's like I can draw or something. I can't draw. Don't let me draw. It's a bad idea. So that diode clampy thing keeps that to plus or minus 1.4 volts. And this is then coming back this way. So what this guy is doing, right, is we have our voltage input here. Hey, look, it's toggling between plus and minus 1.4 volts. This is our plus or minus V in source. And that basically is changing the direction of this integration right here, and we can tap off on this side of the buffer if we feel so inclined. And that gives us a nice triangle wave right there, which is then going to this OTA. Yeah, I forgot some stuff there. Sorry about that. It's going to that OTA there, which then is acting as our comparator, and it's comparing against this wonderful square wave that we've just generated using the OTA. Super neat, right? Turns out you can make all sorts of waveforms with not a whole lot of hardware. So that's the magic of the operational transconductance amplifier, and that's how you get some really cool voltage-controlled oscillators out of that. We now have fun noises, ladies and gentlemen. We have square waves, we have triangle waves, we have sawtooth waves. We're ready to meet the world. But wait, because everybody loves a good filter sweep. I'm really irritating Chris by just like flipping over as opposed to like putting them up here, and it's fun to watch him twitch a little bit while I do that. And unfortunately, because filters are so amazing, I don't have the time to get into like the wonderful depth of all of the classic great synthesizer filter structures out there. There are like diode ladders and really wacky 4-pole stuff that makes strange squealing noises. They're super neat, and we could spend weeks on it. And so I'm just going to like get into the concept of how you might build a voltage-controlled filter. So let's look at a filter. We've seen a pretty basic, low-pass filter right there, right? We got that followed by maybe like a buffer structure. Hey, look, it's a low-pass filter. We got a resistor, we got a capacitor. It's doing something at a frequency that's like cutting off the high frequencies, saving low frequencies. We're good. Except we want to change this. Like we want to, and you could like trim pot that, right, and have a little knob that like changes your filter cutoff frequency, and that's kind of cool. But what if I want to send like a low frequency oscillator into that? Well, I need to change either the resistor or the capacitor. It turns out changing capacitors is kind of a pain, at least in the audio band. You can do it in the RF band pretty well, but no one can hear 2 gigahertz. So we're going to bypass that and drop back down to something you can hear again and say we're going to tweak the resistor a bit. Well, we've got a really cool trick that you can do to tweak the resistor. It requires a little bit of messiness, but you can put a JFET there if you want. And you just need to drive that JFET in like its linear zone. And it has this very narrow band of voltages where it's acting like a resistor as opposed to an on-off switch. And so unlike most modern digital tech, where you're like, we hate that resistor zone and we want nothing to do with it, and we want this FET to be on-off and nothing else, we're now in a world of like, we want that FET to be like a resistor that we can control with the voltage because that's neat. So we could do that, right? That's pretty cool. Right, and then do this stuff. So that's one way to go about it. But we can also use an OTA because we like using OTAs, because why not use more OTAs? Right, so we have, a nice OTA here, right? And we're going to put our audio in here. And we're going to put some control current in here. That's going to be our voltage control for the voltage control filter. And hey, look, we're getting a current output. We're getting a current output for a voltage input. What does that look a lot like? A resistor, right? Like Ohm's law and shit. We have a voltage, we have some thing, we get a current out. Cool. We can now use that to charge up this capacitor, and then that acts like our very basic VCF. So now we have a simple structure for admittedly a 1-pole VCF, and 1-pole is kind of boring, but it still does some cool musical things. And if you want to, you can stack a whole bunch of those on top of each other and get like a 4-pole VCF with some fun resonance and other crazy things, because I mean, like, we're trying to up the cool factor here, and 1-pole filters are kind of lame. But most analog synthesizers will just like stack a whole bunch of stuff on each other and throw hardware at the problem because hardware is expensive. Alrighty, so now I need to talk about a little bit of that magic glue, and I've been like rolling right past this, and just like this is like the train going by at high speed. All of these OTAs, right, have some voltage signal that we're amplifying, and then a control current that sets the gain. But we're not talking about current-controlled oscillators, and we're not talking about current-controlled filters. We want voltage-controlled filters and voltage-controlled oscillators. That's our bread and butter. That's the meat of these things right here. The other thing is that linear is not going to do it for us. We don't like, if you all know anything about human hearing, we don't hear in a linear fashion, right? You go up an octave, you've doubled your frequency. You want to hear something twice as loud, you got to use decibels, and it's all like logarithmic and exponential and kind of a mess. So we need a thing that says, hey, I've got some control voltage here, sends it into a thing, and this does like an e to the x, and then I got a control current out. That's what we need right here. We need one of those guys, because that's super neat. It means that like if I go up a volt here, I get double the current out, and that's super fun. It turns out we've got some great devices that do this for us. We've got some really, really neat devices that do this for us, one of which is called a BJT. Right, and I'm not talking like small signal model here. We're going to like the Eber-Mol, like device physics, intensity. I wrote the thing down here, right? Collector current is equal to reverse saturation current times e to the some constant stuff times your VBE, and then there's a minus one. Woo! Right, yeah, device physics, right? Woo! So we can do that, and it's generally okay for like VCAs and things where we're not super sensitive, right? Like you can shift something by a decibel and you might pick it up, you might not pick it up. But here's the thing, you shift something by like 2 hertz and man, all music is way off. You know, just like a little bit of beat frequencies going on, it's a mess, nothing sounds in tune, we don't like it anymore. So this is cool for some things. Like this works if you don't care about precision too much. Why is that? Because like we got these annoying things, and this is also temperature sensitive, and so like everything's like flying all over the place, and you get 2 degrees warmer, and everything's different. And then like on these data sheets, you have all these like temperature dependent curves, and you can never actually plot a point on those things, and it's just a mess trying to figure out what's actually going on there. So I'm now going to draw something fun. How am I doing on time, Chris? Yeah. I'm guessing y'all don't want me to stop just yet because we're getting to the magic. All right, 5 more minutes, I'm told. So I'm going to throw some stuff at you and try to explain it as best as I can, but I'm also going to try to move a little bit fast here. We're really bad at making transistors to a certain spec. Like, you know, we want a certain beta transconductance in the transistor. We're really bad at doing that precisely. However, we're really good at making 2 transistors, whatever their specs may be, almost identical. And it turns out we can do some really cool things with that. And those of you who have studied like EE 201 or whatever your equivalent course number is, will identify this as basically a current mirror. And I can draw. Right, so that's the starting structure of a current mirror. And this is going to be really, really useful to us. The premise here is that we've tied the emitters together. If we tie the bases together, the currents going through them is the same because the VBE is the same, and there's math. Magic. But what we're going to do is we're going to tie that to ground, and we're going to have our voltage control come in here. And because this is, again, silly voltage sensitive, we're going to do some stuff. Right, hey, look, we've divided it. So we're going to throw that voltage in there, and that's going to shift this current through this thing for us, and that means if we put a current source up here, and I'll get to how that works in a second, we get our nice exponential control current out there. And you can spend like entire semesters on why this actually does what it does. So I'm going to like, magic, it works, mostly. But yeah, so you get this nice control current out, and it works roughly like this. We're going to call this Iref. And then our I control is going to equal Iref times e to the some constant junk. And this constant junk is actually kind of important in device physics land, but and this would be VBE2 minus VBE1, but we've just grounded this guy out and the emitters are the same, so we can actually just call that guy. Hey, look, we've got a reasonably stable current source now. Reasonably. There's only one temperature thing now. We've gotten rid of a whole bunch of other temperature things, which is pretty neat. So yeah, we've got this. We've got some voltage control coming in. We've got a little bit of magic here and a little bit of magic here that gives us a control current. But it turns out building an Iref is not that hard. Hey, look. current source. Neat. I mean, like, this thing is a little wobbly because it's shifting a bit. And the other fun thing is it turns out we don't, like, we kind of care what's down here, but it's not actually all that important. And hey, we can do a thing that compensates that this is wobbling a little bit. This is where I get voodoo-y. So I'm going to like tap off here and send that around this way and throw that into an inverting amplifier, ground that guy out. I'm not even going to like feedback here because, hey, look, I can do that and feedback that way. And it turns out like that as this bounces around, this is now going to bounce around, and like my current source, hey, my current source is stable. Wow, isn't that cool? So I got like a reasonably stable I-reference current now too. Like the collector current on that guy can wobble a little bit, and it's compensated for down there. So here's the other fun thing. It's like I have this V control thing coming in, but I can actually mix a whole bunch of stuff into that, right? Like if I have, you know, some input from a keyboard, right, voltage in, and then I have like some LFO voltage here, and I have, you know, maybe like an envelope generator there that's giving me a cool attack delay response curve. I can, you know, mix all of those together. Throw that into a buffer real quick. And hey, I got a nice mixed together V control here of like the note on the keyboard that I'm hitting and a cool like wobbly LFO or modulation wheel and like a nice envelope generator that's giving me a cool like attack and decay and sustain and release. And that all mixes together. And then that all gets sent through our nice little exponential transition device right there. We're getting exponential current out for our linear voltage in. Here's the other fun thing. If I want linear current out for a linear voltage in, I can throw that guy in there. Right, so if I want like a linear LFO, right, to wobble my frequency, I can just throw that in there, and now I'm getting linear current changes for linear voltage ins. So like, depending on how you wire this guy up, you can get all sorts of fun control signals into the current, going into your OTA, doing that crazy thing with a filter. Isn't that super neat? Alrighty, so like I'm running out of time, and this is why I wanted to be like magic at the beginning, because this is like a super deep, divey world. There's lots of great stuff out there on this stuff. There's circuits upon circuits upon circuits. If you want to nerd out about analog for days, weeks, months, years, there's endless stuff. All sorts of stuff. Chris, I'm going to move this because I'm going back to slides. I can't go back to slides, the police are here. Philip Glass is, or not Philip Glass, John Cage is here to sue us all. Real quick, a slide on some more info. Synth DIY is kind of a hokey homebrew website, but they've got a really great mailing list full of really brilliant people who can be like, why does this weird BJT do that weird thing in that certain temperature? And be like, I know all the physics behind that, and we'll explain it in a very long email that you don't ever want to read. It's a great mailing list for that. There's a website called Muff Wiggler, which is like the forum equivalent of that, and you can ask your crazy synthy questions on forums online. If you just want to like poke around and see what cool historic gear is out there, there's the Vintage Synth Explorer. And there's one of my favorites, which is the Vintage Synth Museum. It's kind of sort of a museum. It's not strictly speaking a museum. It is a place in Emeryville, of all wonderful spots, with the dude behind it, who I feel terrible because I forget his name right now, but the dude behind it will like fix your synths and rent you other really amazing synths. So if you're like, I'm working on a song that really needs an OBXA, he's probably got 10 of them. And you can rent one for a weekend. It's great, and then you two can be Van Halen. There's some great books out there. One of my favorites, which is unfortunately out of print, but you can still usually find, is Electronic Music Circuits by Barry L. Klein. There's the Make Analog Synthesizers book, which is great, but geared towards people with less electronics background. So if you've got a friend who has never soldered a thing before in their life and they're way into synths, and you'd be like, I got a book for you, buddy. That book is great. And then Welch's Synthesizer Cookbook is just like cool, like weird administrivia and other like building fun circuits that make even stranger noises than I was talking about tonight. So with that, in memory of Keith Emerson, who passed recently, unfortunately, and did crazy things with analog synthesizers. Thank you very much. Do I have time for questions, Chris? What's that? Sure. Did I just like throw a whole bunch of stuff at you, or are there questions? Yes, you in the back.
It's kind of random, but like, why are these? I guess they're like in the form of ICs, right? Or are these circuits so sensitive to temperature?
The OTA was built in like the 1960s when ICs were a really brand new thing, and we didn't have good temperature controls for a lot of the circuits that we built. And at the same time, the original op amps were getting built. And it turns out that like op amps are useful for a whole class of problems. Like you can do just about anything you want with an op amp. So a lot of research went into tuning those up and making those stable and doing all sorts of cool things and removing a lot of that variability from them. And it turns out the only thing you can really do with OTAs is make strange noises. And the market for that is cool but kind of small, which is why a lot of the OTAs are just like you're second-handing. Like the 3080 you can still get for like 50 cents a pop, but you're getting it on Russian eBay. And you're not quite sure where it came from or what it was used for. It doesn't matter. You're just trying to make strange noises. So like the OTA is really cool, but not really all that useful for a lot of things. And so it didn't get quite the same development energy that a lot of the op-amp technology did at the time. And this kind of stayed in place where it was.
Yeah, and a question about why you use the JFETs for the integrated resynth. Is that a historical thing, or I mean?
Repeat the question, please.
Sorry, the question is why did I use JFETs to reset a thing? And there's no particularly good reason for it. You could probably get away with using a MOSFET as well. You could get away with using a lot of things. I use JFETs because they're easier to draw. And so I could get through it way faster.
That's a good question. Anybody still use the Clarex opto resistors?
Yeah. So the question is, does anybody still use the Clarex opto resistors? And I'm going to say probably, but I don't know who. Because everybody still uses everything, especially in the world of analog synths where everyone's trying to reinvent the thing that was made 40 years ago with parts you can no longer find. So yeah, probably people are still trying to source those parts and do cool things with them, but I couldn't tell you who.
Do you give day-long talks or week-long or week-long, indoctrination seminars? Join your religion full force without...
I don't at the moment, but I'm actually, there's a professor out of Georgia Tech. Sorry, the question is, do I give hour-long, week-long religion of analog synth talks? And I would love to, but I got rent. But there's a professor out of Georgia Tech named Aaron Lanterman, who's a brilliant DSP guy who also then had a master's degree in music, and so teaches in their EE department, and hasn't taught it recently, but in 2006 to 2010 taught a senior level EE class on all of this. So if you want to spend 4 weeks on VCFs, he did that already, and it was all videotaped, and a couple of people are hosting it online. So you can go and spend an entire week watching a college course's worth of lectures on.
Where do you find that?
His website is no longer hosting it, unfortunately, but if you look on the Synth DIY mailing list, there are people who have posted it there. There are people who have posted, who are re-hosting those videos there that you can then find and download. And unfortunately, it's all in real media format. So I'm sorry, but you gotta suffer for your art.
Hey, we have multi-people players. We don't have to use real media players.
Experience.
Oh,
Yeah.
Okay.
So you mentioned that the transconductance amplifiers have a very, very narrow operating range on a whole bunch of different.
Yeah.
How delicate are they?
They can be pretty delicate and pretty touchy. And so actually, here, I have bonus material. Yay, bonus material. This is just what the gain looks like on a couple of different OTAs over different input control currents. And you can see even that, over the normal range of what you're trying to get the OTA to do is not the most linear thing in the world. So there's, a lot of those classic analog synthesizers have really funky, vaguely detuned, what we call fat sounds, because we never could quite hit the mark on the frequency we were going for. And so we just called it fat, and it sounds sexier that way. I got some really fat bass on this Moog, it's great. And this is why. So you were asking why OTAs nobody uses anymore. This is a large part of why. And this is in the band where they do useful stuff. I guess I'm out of time. One more question.
In terms of the caps, are there any ones that are preferred polyester licenses for them?
There will be analog audio guys and amplifier guys who will get really touchy about the capacitor. Sorry, the question was are there any particular types of capacitors that are better than others? And the answer is yes, but we don't really care. Because we're not building a 100-watt audio amplifier here where we're really sensitive to that. So your caps will degrade over time, and this is why vintage synths have even funkier noises. But for our purposes, we're dealing with enough irregularities in our electronics as is that it's not, as long as you don't let out the magic smoke, you're not going to care too much about ceramic versus polystyrene versus other capacitor chemistries. I know there was a guy here a couple of sessions ago who gave a talk on caps who's probably just raging at me right now. What are you talking about? Capacitor selection is amazingly important. I'm great, cool, buddy. I'm with you on that one for certain things, and this one isn't it. All right, so that's all the time that I have. Again, my name is Funkster. Thank you very much for having me tonight.